Electricity is the force that keeps business running. And like business, electrical power distribution has changed significantly in recent years. Distribution systems and loads in industrial plants and commercial buildings have become more complex. Electronic power conversion equipment, such as variable speed drives, can generate large voltage transients. Other transient disturbances can also be caused by lightning and transmission system switching. When they ride on top of the voltages that supply industrial loads, as they usually do, these transients can reach peak values in the thousands of volts. The consequences can be devastating, particularly for someone taking measurements on the electrical system. The danger from these transients is very real, but the hazards can be minimized. The key is to have the right tools and follow the proper procedures. As you watch this program, keep in mind it's only an introduction. There's no way we could cover all the safety information you need in 20 minutes. Be sure to read the instruction manual that comes with your meter for additional safety information. First, we'll review the latest international safety standards. Next, we'll look at some of the hazards when you're taking measurements on power circuits. Then we'll show you how to find out if your digital multimeters meet current standards and how meters are tested and certified. Finally, you'll see how making safe measurements on electrical equipment requires both the right tools and safe work practices. To provide better protection for users, the International Electrotechnical Commission, or IEC, has introduced more stringent standards for low-voltage test equipment. For the first time, these standards differentiate the transient hazard by location, as well as the voltage level. IEC defines 4 categories of overvoltage impulses. The rule of thumb is the closer you are to the power source, the greater the danger, and the higher the overvoltage category number. Transients are not as dangerous in lower categories because lightning or other high-power transients will be dampened as they travel through the cabling and equipment in a building. Remember, in general, the greater the short-circuit current available, the higher the Cat number, and the more hazardous the transient. Cat 4 is associated with the origin of installation. This refers to power lines at the utility connection, but it also includes any outside cable runs, since they could be hit by lightning. Keep in mind that IEC 1010 covers systems of 1,000 volts or less, which is considered low voltage. Cat 3 covers distribution level wiring, which is where most electricians work. This includes mains circuits, such as three-phase bus and feeder circuits, load centers, and distribution panels. Permanently installed loads are also Cat 3. Cat 3 includes big loads that can generate their own transients. Cat 2 covers the receptacle circuit level and plug-in loads. And Cat 1 refers to protected electronic circuits. Some installed equipment actually includes multiple categories. This lighting control panel is Cat 3 on the 277-volt power side and Cat 1 on the 24-volt DC side. In environments like this, you should use the higher-rated Cat 3 meter. Let's take a closer look at why transients are so dangerous. In this example, a service technician is making a phase-to-phase voltage measurement on a live motor control circuit. This is a Cat 3 environment. A transient, due to a nearby lightning strike, was large enough to cause an arc to strike inside the meter. Short-circuit currents as high as thousands of amps can flow for several milliseconds. At these current levels, the tips of test leads superheat, and the handheld probe tips start to burn away, drawing an arc from the contact point to the probe tip. The tech sees a bright blue arc flash and at the same time is startled by the bang of the arc exploding inside the meter. The arcs follow the vaporized test probes. If these two arcs join as the tech pulls away, one large arc is formed that provides a low-impedance path directly from one electrical phase to another. When two arcs join, they cause a phase-to-phase fault. The result is an arc blast. The energy in the electrical system can fuel a plasma fireball. Temperatures can reach about 6,000 degrees Celsius or 10,000 degrees Fahrenheit. Here's an actual arc blast. These fuses were purposely misapplied. They're designed to interrupt 10,000 amps of fault current, but are installed on a 50,000 amp circuit. A dead short was created on the load side of the fuses. Transients aren't the only source of arc blast hazard. In fact, one of the most common misuses of handheld multimeters can cause a similar chain of events. If the user leaves the leads in the amp's input terminals and then accidentally connects the meter leads across a voltage source, he has just created a short. While the voltage terminals have a high impedance, the amp's terminals have a very low impedance. That's why the amp's terminals must be protected by fuses. These fuses are the only thing standing between that user and a potential disaster. If the meter is fused and fused correctly, the result will be a blown fuse, a small price to pay. Never replace a blown fuse with the wrong fuse. Only use high-energy fuses specified by the manufacturer. These fuses are rated at the same voltage as the meter, and some can interrupt fault currents as high as 100,000 amps. Here's a meter where the specified fuse was replaced with a low-energy automotive fuse. Fortunately, the meter took the brunt of the explosion, and the user escaped serious injury. Meters should be tested to see if they can survive high-voltage transients. A special test machine is used to generate the overvoltage transient and fault current, as defined in the IEC 1010 standards. The meter is marked Cat 3 1000 volts on the front of the case by the manufacturer. But more importantly, it has been certified by an independent testing lab. A Category 3 1000-volt meter is required to survive a minimum of 20 transients of 8 kilovolts without permanent damage. As a short test, we are programming the test machine to increase the transient voltage in 1000-volt steps until the meter fails. 6,000 volts, 7,000 volts, 8,000 volts, 9,000 volts, 10,000 volts, 11,000 volts, 12,000 volts. This meter finally failed at about 12 kilovolts, which easily exceeded the minimum of 8 kilovolts. Some manufacturers state that their products are designed to meet or conform to standards, but not every meter that makes that claim will pass the test. Here's what happened to a meter marked Cat 3 1000 volts when it was actually tested. Remember, the meter is supposed to withstand a minimum of 20 8-kilovolt transients. This meter failed twice before reaching 8 kilovolts, once at 7 kilovolts and again at just under 8 kilovolts, with a fault current of 2.8 kiloamps. These resistors were destroyed. These are burned traces and arcing between traces. If this had happened on a power circuit, the results could have been disastrous. How could a meter marked Cat 3 1000 volts not pass the standard test? The IEC is not responsible for enforcing their standards, so a meter that claims to be designed to a standard may not have even been tested. That's why it's essential that a digital multimeter you use has a label that shows it's been certified by an independent testing laboratory, like UL in the United States, CSA in Canada, TUV in Europe, and so on. In addition to the right kind of transient protection, a meter should be able to withstand accidental overloads. Look for a meter with overload protection on the ohms function. The circuit automatically recovers when the overload condition ends. To minimize the danger of electrical shock, use test leads with shrouded connectors and finger guards. Test leads should be certified to a category and voltage as high or higher than the meter. Both meters and test leads should have double insulation, as shown by this symbol. Look for a meter with recessed input jacks and high-quality non-conductive case materials. All these important safety features should be protected by a tough, industrial-strength outer case. It seems obvious that a meter should survive a fall from a test bench or work ladder. Safety results from using the right tools and safe work practices. Whenever possible, work on de-energized circuits, and always follow proper lockout-tagout procedures. Make sure you use the right tools for the job. Use a meter that's rated for the overvoltage category and voltage level you're working on. Practice one-handed measurements. Follow the electrician's old advice, and keep one hand in your pocket when you can. Always connect the grounded lead first, the hot lead second. Disconnect the hot lead first, the grounded lead second. Use the three-point test method to make sure your meter's working. To do this, first test a circuit known to be live. Measure the target circuit. Before concluding the circuit's dead, retest the known live circuit. This way, you know your meter's working. Use well-maintained tools and appropriate safety equipment, including safety glasses, insulated gloves, insulated tools, insulating mats, and don't work alone. These are just a few tips to make your measuring, troubleshooting, and repair go smoother and safer. Insist on instruments that carry the emblem of an independent testing lab.
Look for these Fluke meters that are built and tested to meet safety standards. The Fluke 89.4 offers top performance in a high resolution, high accuracy, true RMS DMM. Included among its many features is a dual backlit display, min-max record with real-time clock, an optically isolated PC interface, and logging capability for storing up to 1,000 readings in its internal memory. The Fluke Model 87 Series 3 handheld multimeter measures true RMS voltage and current. It also features frequency, heat, and min-max measurements. The Fluke Model 26 Series 3 true RMS analog digital multimeter offers high performance and true RMS accuracy. The Fluke Model 12B and 7600 simplify voltage measurements in power environments by automatically selecting the correct function. The Fluke T5 tests for continuity and measures resistance, AC voltage and DC voltage. The open jaw quickly measures AC current. The T5 is available in 600 and 1,000 volt models. The Fluke clamp meter family includes the Model 31 and 33 clamp meters, which provide true RMS measurements of current up to 700 amps. The Models 30 and 32 are rugged, self-contained, general-purpose clamp meters, providing AC voltage measurement and current measurements to 600 amps. The Model 36 offers both DC and true RMS AC measurements, as well as max hold for measuring inrush current or peak load. The Scope Meter 123 is versatile and easy to use, with its connected view technology for triggering a wide variety of signal patterns automatically. It's the ideal choice for troubleshooting industrial machinery, instrumentation, control, and power systems. The Scope Meter 190 series are high-performance oscilloscopes with up to 200 megahertz, 2.5 gigasamples per second real-time sampling per input, and 1,000-volt Cat2, 600-volt Cat3 fully isolated inputs, including the latest innovative features like Connect and View, Scope Record, and capture and replay of 100 screens. The Fluke Model 867B graphical multimeter offers highly accurate, direct measurements, waveform displays to 1,000 volts. The Fluke Model 39 power meter and Model 41B harmonics analyzer combine visual feedback of an oscilloscope and the power of a harmonics analyzer. The Fluke 43 power quality analyzer is optimized to maintain power systems, troubleshoot power problems, and diagnose equipment failures. It combines power quality, multimeter, and scope capabilities in one tool. Rely on Fluke for rugged, reliable tools. Fluke, keeping your world up and running. If you'd like to get connected to a group distributor near you, or you'd like additional copies of this tape, call one of the following numbers: